So good morning, and thank you for attending the Geospatial Imagery and Data for Forestry Applications webinar. Just before we begin, I'd like to take just a couple of minutes to go through some housekeeping items. So first of all, my name is Owen Cox, and I'm a programming consultant here at Exospheres. So first I want to be sure everyone can hear me okay. So please just enter yes or I can hear you in the questions box so that we can see everyone can hear okay. Also, you should see on your screen a slide that says Geospatial Imagery and Data for Forestry Applications. If you don't see that, please let me know. Okay, I can see lots of yeses, this is looking good. I'll take some time after the presentation to answer some questions you might have, so please save any other questions to the end. And with that, let's get started. This presentation is split into three sections based around ways to use geospatial imagery and different data types to solve some forestry applications. To do that, we're using ENVI LIDAR and ENVI Sarscape as our platforms to work with multispectral, LIDAR and SAR data respectively. Now the goal is to demonstrate some ways in which these data are used and also the tools to solve some common forestry problems. The three scenarios we'll look at are summarised here. The first scenario will look at ways to use multispectral imagery to prioritise reforestation efforts in an area affected by wildfire. The second scenario uses ENVI LIDAR to perform automated feature extraction of trees from point cloud data to count the trees within a plot and also utilise attributes such as tree height for biomass and timber volume assessment. And the third scenario focuses on ways that some of our customers are using SAR data in forestry applications such as cut block delineation, classification and timber volume modelling. As I said, this first scenario will use our ENVI platform to investigate the wildfire scenario which I just described. So let's get started. For scenario 1, we're using ENVI to determine priority for reforestation in a burn area. What you see here is the ENVI interface with an image displayed in the western foothills of Boulder, Colorado. This image is a 2008 ALI MSI image that was required before a large forest fire. A couple of things about the interface. To the left of the main display is the layer manager where you can see a list of all the files in the layer display. Note the ability to pan, zoom, adjust contrast, etc. by way of these buttons at the top. Here I've loaded an image of the same area after the fire. You can see the fire scar in the centre of the image. By moving the transparency slider, you can look from one image to the image below. And that's just me sort of adjusting the transparency slider at the top. On the right you'll see a toolbox, which will be used a little bit later on in the exercise. And here I'm just showing a portal window opened, looking through the image on top to the image below. So far we have data that have been calibrated to the sensor, but have not been atmospherically corrected. Here I want to take a look at two images side by side to talk a bit about atmospheric correction. So first I want to clear my display by removing all layers. And this is now my clean screen. Then I split my views into two vertical views, and note you can look at as many 16 views at once. Next open the data manager to see the list of files I have open. I'm going to load a colour infrared composite of the same image both before and after atmospheric correction. And finally I load my images into each view. What you can see on the image on the left is the colour infrared composite before atmospheric correction. On the right is the colour infrared composite image after atmospheric correction. At a glance it's difficult to tell the difference between the two images. So while I'm not going to spend a lot of time talking about data pre-processing and calibration today, I do want to mention it as an important topic, especially when comparing data that were collected at different times. The goal of atmospheric correction is to remove atmospheric effects that are caused due to the nature of solar radiation moving through the atmosphere to the sensor. In this case, to accomplish atmospheric correction for these images, I use QAC, which stands for Quick Atmospheric Correction, and is part of the ENVI Atmospheric Correction toolbox, although there are several algorithms to choose from. Now I've linked these displays so that the spectral profile we're about to see is over the set of the same pixel, which is a vegetation pixel from each image. So you can see the reflecting spectra on the right looks like you'd expect a vegetation pixel to look, whilst the one on the left indicates some of the atmospheric interference which I just mentioned. So far we have the before and after imagery, and now I'm going to bring some additional data for our analysis. First is a DEM corresponding to the same area. That stands for Digital Elevation Model. And I also have ArcMap open and happen to have a vector delineating the burn area as part of my geodatabase. So using the GeoLink to Arc, I can then link ENVI and ArcMap together and pan, zoom, so on. I can also drag and drop files from Arc, but in this case I'm just going to choose to import the vector directly from the geodatabase. So here we are back in ENVI, and I'm going to open up a remote connection. I select New and into my file geodatabase, and then select the file. And now I can use that vector to subset my DEM and my imagery by constraints of this study area. To subset by a vector layer, I can simply go to my toolbox, type subset, and select the appropriate tool. I'll then select the file I want to subset, click OK, and select the burn extent shapefile, which delineates my area of interest. The new image subset is displayed, and I repeat the process for my atmospheric corrected image layers. As you can see here in the Layer Manager, I now have a layer stack of my image before and after images, as well as the DEM subset. And now the final step of pre-processing is going to be to create a slope map of the DEM to identify the areas of high slope. Areas of high slope tell us where there is the greatest risk of erosion and potential priority areas for reforestation to mitigate flooding and other potential hazards within the area of interest. To do that, we open the topographic modelling tool. Now for this analysis, we're going to create a slope map in degrees. And now we've displayed the slope map in the main display area. But we only want to process areas with greater than 25 degrees slope. So to process only those areas with a high slope, we create a mask of slope greater than 25 degrees by utilising the raster colour slice tool. First we remove the default slices, which span the entire range of the data. Then we add a slice to only highlight areas with greater than 25 degrees slope. When I click OK, only the areas having a greater slope than 25 degrees are highlighted. Those results are saved and we'll use them in the next step. Now we have our subsets of the before and after images within the study area, as well as a slope map highlighting the areas where there is a steep slope. To perform the final steps in our analysis, we use the change detection workflow in ENVI. ENVI workflows are processing steps to accomplish a specific task that string together analysis steps in a wizard-based interface. The idea behind workflows is to ensure that robust image analysis algorithms can be applied to the data in the same order every time, which drives accurate and similar results from analyst to analyst. Now for this example, we import before and after images as time 1 and time 2, as well as the slope map we just created. Next, we have the option to automatically register images for direct pixel-to-pixel comparison. Then we have an option to look at an image difference, which is a band-to-band comparison, or an image transform, which includes algorithms such as principal components analysis, maximum noise fraction, and independent components analysis. In this case, we're going to use the Normalized burn index algorithm, which is a feature index difference. Now the normalized burn ratio is derived from different wavelength bands. So in this case it's the ratio of the difference between the near infrared and the mid infrared over the sum of the near infrared and mid infrared. We have the option to threshold the image or just to export the result. In this case we'll just worry about exporting the result. And again, we apply a colour raster slice to to the results, this time using a colour ramp across all the data. This enables us to identify locations which have high burn severity and also a high slope a high intersection between the burn severity and the slope. And this is our final result. And from here you'd have the option to write the results directly to your geodatabase, or you can export it to ArcMap. You can save the result as any different number of raster formats, including GeoTIFF, or you can just, if you want the image for a presentation, you can always just ship it to PowerPoint. In this case, I decided to save results to one of my ArcMap templates. So now at this point, I'm just going to pause for a quick poll. Now we've looked at some multispectral imagery. So we'll just take about 3 minutes to put up a polling question. So while that's up, please feel free to refresh your coffee or whatever you need to do. And the polling question has to do with our utilisation of the spectral information we used in this example to run a normalised burn index. I'm curious to know the types of data you work with or are planning to work with in the next 12 months. Which of the following statements best describes the data you plan to work with or are currently working with? I use or have plans to work with 3-band red, green, blue data, or 4-band, which tends to be RGB and near-infrared. I have plans to work with and utilise Landsat 8 data. I use or have plans to work with SAR data. And I use or have plans to work with hyperspectral data. So I'll just make that polling question available now. So the poll's now open. I'll just give you a few minutes to have a look at that and refresh your drinks, and then I'll get back to you. Oops. So the next scenario, we utilise our ENVI LIDAR product to look at automated tree count in a plot, automated feature extraction from LIDAR data, as well as deriving forest statistics that go into building biomass and timber volume models. So in this scenario, I'm going to showcase some of the ways that ENVI LIDAR works seamlessly with ENVI and ArcGIS to provide a complete platform for end-to-end LIDAR data analysis. So in this example, we're going to look at a last point cloud data over Western Boulder, which is just a little bit southwest of the fire area near the Flatirons, which is just outside our headquarters in Boulder, Colorado. Now we're going to look at using ENVI LIDAR to automatically extract some elevation products, as well as treating our point cloud, and do some analysis including creating a canopy height model and some simple volumetric biomass calculations. So let's take a look at the interface first of all. Here in the main display we see a section of our point cloud coloured using a rainbow colour map. In the lower left area we see the navigation window, which displays a low resolution elevation map of the area. The portion of point cloud in the main display is encased by this pink bounding box. The log window tells us things about our processing and view. Also note the toolbar at the top. This is where we access settings like our production parameters, as well as quality assurance mode features, which enable us to look at derived products such as contours and objects such as trees, as well as perform point cloud editing like point reclassification. Now this file doesn't have RGB values, but if it did, we could use those values to see a true colour representation of our point cloud. So here the point cloud is just simply colour by height. When first ingesting a point cloud, it's a good idea to look at the density map, which will indicate the density of your point cloud. So let's take a look at the density map of this point cloud. What we see here are areas of greatest point density, which are red, where greens to blue are areas with lower point density. On the right, the density under my cursor is reported, which in this case is 32 points per metre square. In terms of automated feature extraction, upwards of 10 points per square metre is generally very good for tree extraction, although obviously the more the better. For general geomorphology, such as DEMS, DSMs and tin surfaces, a point per metre square is generally sufficient. But for power lines and finer features, you probably need in the teens to 20s, and for buildings, 5 to 10 points per metre squared is probably a good place to start. After I close density map, I can set my production parameters. Now the production parameter properties contain 3 different tabs where I can change settings based on my desired output. Here I'm selecting to produce an orthophoto, some elevation products including a DEM and DSM, which we use to create our canopy height model, some tree vectors, and note the export I have as a shape vector file, and some other features as well. I also set my input coordinate system here. And here I'm selecting a subset of my point cloud for processing. I could process the entire area, an area of interest is indicated here, or I could import a vector layer to constrain my processing. I can also import a centre line. An example of when I might use this feature is if I'm looking at potential tree encroachment down a power line corridor. I might import my corridor back to the centre line and then process my last data set just along that line to focus my study along the corridor. Now the area delineated here represents the first part of our scenario, where I'm trying to get a tree count within a specified plot. The plot boundary is also shown as a white square in the image above. Now the final step in my production parameter settings are setting specific properties about each product I'm extracting from the point cloud. For example, in the trees parameters, I can specify a minimum and maximum height to exclude things like shrubs or other points that I might consider outliers. I can also constrain the minimum radius, for example to avoid classifying power poles as trees. I might also want to constrain the maximum. By decreasing this number, I get more granular separation in areas which have dense canopy cover, thus enabling clearer tree crown delineation. Note that each data set is unique, and therefore modifications of these settings are data specific. Now we can also modify the resolution of the DEM and DSM, clip points to exclude things like birds, so on. Now once processed, if I open the QA mode to look at the processed data, note that various vector features were derived, as well as classified points being displayed. Another important statistic that we've got reported here is the total tree count in the processing area, which is exactly the metric we're looking for in this scenario. Now the output log reports 725 trees were found in the area of interest. So a few things to note about the interface before we move on with our biomass example. QA features in this view can be turned on or off by selecting and deselecting these checkboxes. And here I've deselected the points and displayed the tin surface, just this wireframe. I can also redefine my display area and view a solid terrain. And in QA mode I can also look at a cross-section, which is what I have here. One problem many people have when working with LIDAR data is that points are not always classified properly, and it's useful to be able to reclassify points or make other adjustments. Now, an ENVI LIDAR does just that, so I don't want to spend too much time on cleanup, especially because this data set doesn't have too much noise. I do want to take a moment here to show you how we might do that. As you can see, there is a tree in the centre of this cross-section that was missed, so I'm going to make a correction. First I double-click on the tree and select New Correction. Now I can set a tree at that location. And modify the radius and height. I can do this for any tree until I'm satisfied with my edits. Then when I reprocess the data, these points are classified correctly. So moving on, I exit QA mode and I want to take a look at some of the derived products to perform our analysis. Biomass calculations and timber volume modelling require inputs such as tree height, crown height models, and other parameters we'll drive next. To do so, first note I launch ENVI LIDAR derived products in ENVI and or ArcMap directly from ENVI LIDAR. First I'm going to choose to launch the products in ENVI by simply selecting the products which I wish to include. And here we're looking at the products in the processed area launched in ENVI. Here we see the DEM as a base layer with contour vectors in green and tree vectors represented as red symbols. Now the first thing we're going to do is use the DSM and DEM LIDAR product to create a canopy height model. Now this is based on the paper. We subtract the DEM from the DSM to derive the canopy height model, CHM. And to this in ENVI we use bound map. And simply enter the expression B1 minus B2, which is band 1 minus band 2. And the output of this is our canopy height model. So here is this canopy height model, CHM, the output, which can be used as an input to model biomass. And I just want to make a side note here to acknowledge that most forest volume and biomass estimations rely on several variables, including robust and sometimes complex algorithms and models. And to that end, I want to highlight a paper here by Simon Popescu, who has done quite a bit of research in the software development to build such models. The reason I'm highlighting the paper above is based on two things. Now the first is that the model he outlines is based on determining crown diameter, and if you'll notice, the input for this is the CHM, the canopy height model. So I want to highlight that our LIDAR product cloud, our LIDAR point cloud, and the automatically divide products we've just created can serve as an input for this process. And the second important thing I want to mention here is the remaining piece of this model are algorithms implemented in IDL, which is the programming language upon which ENVI and ENVI modules are developed. Now, IDL is an interpretive programming language used widely in the scientific community in its own right, but also underpinning ENVI. The ability to add custom functionality using time-tested and scientifically based processing algorithms that are accessible to non-programmers, while IDL an interpretive programming language, as I said, that looks much more readable than native code such as C or C++. And what I'm showing here is this IDL development window. In this example, I'm creating a tool to be used in the ENVI environment, which will create the CHM. So the work we did with Biomass, but this will be done automatically. Now the code will tell ENVI to ask the user to import a DSN and a DEN, and will calculate and display the canopy height model. Another button I might add would be to get crown diameter with code written based on the model we just saw. Then I could simply compile the code, restart ENVI, and from this new ENVI session, if I click on the extensions window, the extensions folder, and we can see my new functionality is seamlessly integrated into the user environment. So not only can I use it over and over, but now others can share the work that I've done as well. So now we'll just go back one step. I'm bringing up this graphic again to highlight our user contribution site, where people share these extensions and custom functions all the time. But getting back to our forestry example, now the takeaway message here is that robust algorithms to build solid models and make robust calculations in many cases already exist. And the input needed to make model-based biomass calculations are easily derived from the last point cloud data. One more example worth noting as we get back to our discussion of utilising LIDAR data in forestry applications is another recent paper noted above, which also uses this canopy height model for LIDAR-based timber measurements. The illustrations I pulled from the paper show the ability to measure the crown length and width directly from the CHM, which are variables that go into the own model. Spoiler alert to this though, if you were planning on reading it. In the conclusion of the paper, a positive correlation between diameter at breast height, which is dBH, and LIDAR-derived tree height and crown parameters was established. Now what that means is that standard timber volume and biomass calculations can be used for common forest management tasks, such as LIDAR data and its derivatives as valid input. And before we move on entirely from our LIDAR example, I want to go back and export a couple of products into ArcMap and show you one more thing. Here we have the bitmap image as the base layer and the tree shapefile vectors represented here with green dot symbology. Note that when I open the attribute table, both the height and radius are maintained for each tree. We can look at statistics for height and radius, for example, and also use this information to calculate a rough volumetric estimation based on cylindrical volume. Obviously the volume is pi r squared times the height, and which for this data set the answer will be in cubic meters. So that's just a quick example of an example of what we might use ENVI LIDAR for and LIDAR data for a forestry application. So let's just take another couple of minute break here while I put up our last polling question, which in this case will be about LIDAR for forestry applications. So what problems do you envision solving using LIDAR analysis in the next 12 months? Tree counting, biomass or timber volume modelling, topographic analysis of digital elevation models, automated feature extraction of trees, power lines, buildings, and point cloud editing and reclassification. So I'll just put that polling question up now. So just in our last section, I want to take a little bit of time to talk about some of the ways which many of our customers are using SAR data for their forestry applications. Now we're seeing an uptake in SAR data for forestry across Europe and expect to see similar trends in the States and across Canada and other markets in the short term. The goal here is just to convey some different types of SAR data being used in forestry applications and outline a few of those scenarios. Now remember from a few slides ago, SARscope is a module to the ENVI platform. Now the use of SAR data is typically seen for interferometric processes such as dam creation or for displacement mapping for things like land subsidence, etc. In this presentation we can talk about how the use of amplitude and coherence data from SAR images can be used to extract useful information for forest management. Now with SAR data we'll generally use multi-temporal images, particularly in the generation of coherence images. This is a different concept than optical imagery, in that pairs of SAR data covering the same image in a different time period are used to generate coherence images. The results can be similar and in some cases superior to those of optical data. Now this diagram shows the workflow that we're going to discuss. So the goal is to extract biophysical information for forest management, such as tree height, diameter, breast height, dBH, basal area, timber volume, trees per hectare. Now we're using SAR data with ground truth to extract this information. Usually the information is collected manually and this process is very expensive. Field data are typically collected in sample areas and are therefore represent an estimation of the total area. SAR data used in conjunction with field data can help give a bigger picture of what's actually happening across the entire study area. Now the following example discusses the processing required for single SAR images in order to reduce speckle and produce an image with better quality for further analysis. So this is an example of an original Cosmos SkyMed strip map dataset from South Africa which doesn't have any filtering applied. You can see how noisy the data is and how difficult it is to determine what the features are. The image has been geocoded and radiometrically calibrated and normalized. With filtering, we're able to improve the quality of the result, as shown in this same Cosmos SkyMed image. In this case, a Gaussian distribution entropy map filter was used. Now this is the same dataset with an additional level of filtering. In this case, an anisotropic nonlinear diffusion filter was used. You can see how the features in the dataset are becoming easier to distinguish. This also makes it easier to segment or classify the data with ENVI. And this image represents an RGB composite of an ALOS pulsar dataset. This is a combination of two polarizations, horizontal-horizontal for the red band, horizontal-vertical for the green band, as well as arctan of horizontal-horizontal over horizontal-vertical for the blue band. You can see the forest is well characterized in this type of color composite. The intact forest is shown in bright yellow, but you can see the bottom right side of the image, an area of lighter yellow with some fracturing that looks like a field. This actually represents an area of later regrowth of the forest. In the brown and blue areas, you can see clear cuts and early regrowth of the forest. You can also take this image and segment or classify it with ENVI to extract only the forest polygons for further analysis. ALOS pulsar SAR data uses the L band. Now this is very good for penetrating forests as it's a longer wavelength. There's very little saturation of backscattering values. You can then correlate backscattering values with ground truth data to establish a model estimating the volume, trees per hectare, that sort of thing. You can't do this type of analysis with Cosmos SkyMed as the X-band doesn't penetrate very well, but you can use Cosmos SkyMed data for other types of analyses. This is an example of ENVI ASAR data. Once again, this represents a colour composite using two polarizations. ASAR data uses the C band, which is a mid-wavelength band for SAR data. C-band data is harder to use than L-band data for timber volume estimation because the signal is not well saturated. In general, it's hard to use ASAR or any C-band data for forestry types of analyses. Theoretically, you could use the P-band for forestry, but there aren't any instruments available yet for this band. And this image represents an RGB colour composite of Cosmos SkyMed data. It shows it's really hard to use polarisation combinations with an X-band dataset to get viable classification results. The regrowth area is mixed with standing forest and it's not easy to separate or segment classes. So we need to use Cosmos SkyMed or X-band data in a different way for forestry applications. In this RGB colour composite of the same area, two Cosmos SkyMed images taken one day apart are used to calculate coherence. Now, because the data was collected one day apart, there aren't many changes to the overall area in general. So coherence is really low, except for areas with vegetation. Now, vegetation typically has high backscattering with low coherence. In this image, vegetation is represented by the dark green areas. At the right side of the image, up towards the centre, there's an area that is light green in colour. This represents new regrowth. Red represents bare soil. You can see this type of analysis is much better for separating classes with X-band data. And just to bring that all together, this slide represents a comparison of what you can see with each of the three sensors. Even if the information for each sensor is acquired with different time periods, the sensors can give you an idea of what changes are happening for a particular area. The ALOS image shows the standing forest in yellow in 2008. In the ASAR image, if you look at the lower right corner, you can see the blue area that represents a clear cut in 2010, but you can't really tell the actual state of the forest. This is the Cosmo from 2009. You can see the clear cut area, but you can also tell it's regrown, which you can't see in the ASAR data. We're now going back to the South African forest area. So this shows the detailed processing steps involved in the creation of this image, so the selection of filters. And this image now shows how easily we can form a segmentation. So you can very well here see the vectors which delineate different shapes in the image. And now classification has been run on this segmented image, which very clearly highlights the bare soil region. So we can see bare soil around here in sort of browns and oranges, and the forestation areas in the dark and lighter green. Now we're going to do the same thing for the Cosmos SkyMed image. So again, we'll just look at the processing steps that are required to produce this image, so the filtering, registration, and this time the coherence generation. And running a similar classification, we can see the bare soil again, which this time is orange and pinks, and forest areas in green. And this is an example of the same area acquired 1 year apart with the ALOS Pulsar image on the left versus the Cosmos SkyMed image on the right. If you look about a third of the way up the image, you can see, you can see a small dark body of water to the left of the image, which is about here. And if you look down a bit, you can see a blue path going around a red speckled harvest area. You can see the same area in the ALOS dataset, and in this case it's represented by a brown and yellow area. The areas are clear cut, it's easily extracted using the decision tree classification tool in ENVI. At the top right corner of the Cosmos SkyMed image, there's a big rectangle with red and green clear cuts. You can also see this in blue in the ALOS image. In this case, the Cosmos SkyMed dataset suggests this is a regrowth rather than a recently harvested area, clear-cut area due to the speckle look. Now, tree growth in South Africa is 10 times faster than the US or in Europe, so trees can grow as much as 6 metres per year. So you can see changes in regrowth within a single year using SAR data for this area. And here's an example of segmentation of both images. You can establish semantic attributes for these segments. And now running a classification, again we can see the classification results difference between the two images. 15 metres resolution for the ALOS dataset versus 3 metres for the Cosmos SkyMed dataset. So as you can see, this resolution is a lot coarser in the shapes, whereas here we've got a lot finer. And this diagram shows the workflow to extract biophysical parameters from SAR data. With the addition of ancillary data from ground truthing, we can extract timber height, diameter of breast height, and basal area. And this uses pulsar data and field data. For forest model creation, rules are different for different species and so on. The creation of forest model requires knowledge of the area and the types of trees which are going to be present in that area. So now the next series of examples show SAR data analyses from a natural forest in Russia. So this image represents a classification image result of a huge area of AOS pulsar data from Russia. The decision tree classification method for ENVI was used in this example. So again, same sort of classifications as before. We can see the vegetation areas and bare surfaces. And the image shows just how easy it is to detect clear cuts and changes using the L-band ALOS pulsar dataset. You can easily see the taupe and beige areas of the clear cuts. In this case, a temporal sequence of images were used. So they were defined as clear cuts prior to 2007, between 2007 and 2008, and between 2008 and 2009. In this image, you can see the different shades of reds and browns for clear cuts, but you can't get into all the info that all foresters might need. So for example, you can't see if there are standing trees inside these clear cuts. In many cases, foresters have to leave a certain percentage of seed trees, so it would be good to identify the trees in the harvest areas. Using Cosmos SkyMed data at 3 metre resolution, you can delineate the seed trees inside the clear-cut areas. You can take this information and do a volumetric calculation on this to determine the percentage of seed trees in a clear cut. And this is an example of the same image with segmentation applied, highlighting the seeding trays. So thank you for joining me for this presentation. I hope it's given you a good idea of some of the capabilities of the ENVI range and products and some of its applications in this field. And I'll be happy to answer some of your questions now, so please enter them in the text box. Any detailed questions will be noted and I'll get some responses out via email. And also up on the screen here, we've got some of the ways you can find out more information. We regularly update the website with new blogs and info, so it's definitely worth keeping an eye on that. And the social media site's a great way of keeping up to date with editions. So I'll take some of the questions now. Thanks.